Does it work?
No, you still share the presentation, the presenter's view.
All right, so if I can change.
So I guess you have a control bottom right that could probably take you to full screen.
Does it work now?
Yes, and press that one where you are. Yes, we got it.
All right, so
Okay, so
was more difficult. All right, so do I need to start, Manolis?
If you allow me to say a few words based on
please.
what I received from you, so that we get people tuned in. So Matteo has been involved in several, actually many HPC systems that were co-designed, and we heard him express his opinion yesterday about the rationale for doing application-specific co-design, and among other systems that were actually deployed worldwide. Matteo was contributing to Quadrix, QM1 and QM2. He has contributed to the array processor experiment, APE100 and APE1000. I understand at that time he was very much working with the APE lab in INFN. Is this correct?
Yes, I was working with Nicola Cabibbo and Nobel Prize winner Giorgio Parisi, and I helped these two outstanding scientists in order to design all the APE families. I will say the APE family of the computers that we designed for QCD at that time. I mean, a very long time ago, at the beginning of my scientific career. Yes.
Right, and Matteo has had contributions, hardware contributions to the trigger and data acquisition systems of, let's say, the LEP, LEP experiment and the LHC, and even has done work with embedded radiation-hardened technology. So, as quoting again, this maker's mentality and the co-design towards a challenging target. I think this has been a guiding principle in his career. And I think he has a lot of experience in that path, but also a lot of, shall we say, interesting snapshots to show us. So the presentation is titled, Where is Gone Co-Design? I assume that he will express his opinion now. Thank you for taking the time to be with us. Please go ahead.
Thank you, Manolis, for the outstanding, I would say, introduction. Thank you very much. Thank you very much for your invitation. And for me, it is a rare and outstanding privilege to be here with you. Unfortunately, in a remote way, because, you know, the European Union is supporting the Green Deal, so we tried not to move too much in order to be in line with this European Union policy. I'm going to share with you some observation from my privileged, I will say, point of view, but I'm not talking on behalf of EuroHPCJU or the EU in general. This is my very humble and personal opinion about the status of the art of the co-design. So in fact, I was going to present some examples of co-design in our projects, and at the moment I'm dealing with more than 40 actions, so I have an overview quite wide of what I will say of the status of the art. But then I ended up with this question, where is gone the co-design? Because you mentioned my my contribution, for instance, to the supercomputers designed by Nobel Prize winner Giorgio Parisi and Nicola Cabibbo in Rome at the beginning of my career. And that was a real co-design, I would say, because we shaped the whole supercomputer in order to achieve a very specific objective. So to develop a machine that was able to perform very well in the so-called QCD calculation, so very specific to a specific objective, scientific objective to be achieved. So I will start from the classical definition of co-design from Patrick Chaumont, that is a classic book, I would say, in co-design, hardware and software co-design. So the hardware and software co-design, according to Chaumont, is the design of cooperating hardware components and software components in a single design effort. I stress the single design effort because this should be bear in mind when we think about the co-design. Then the situation that I see in from my privileged point of view, I see that sometimes the co-design is mainly a mere software optimization, so tuning the codes, the hardware that we buy, basically, or a platform that we buy, and then we try to optimize some software. Because I notice that sometimes the hardware is bought as it is and then installed, merely installed. As I said, the software may be optimized, and sometimes in hardware, the hardware agnostic approach in software are used. For instance, Cocos, all the tools that and the software that you know better than me are used. So the hardware co-design, where is it? Because I rarely see a real effort in order to change the hardware in order to optimize the software that we are going to run. My observation is that the software and the hardware are still more glued together rather than co-designed. And I will express some example. For instance, the co-design that I see is sometimes just an add-on. Basically, we have on the market a lot of very different and very efficient and very expensive FPGA-based accelerators that we can buy. They are normally PCI Express board, and we can install these boards in our hardware. And then, of course, by using specific software, we can use this FPGA technology as an accelerator, basically for some part of our software. But I would say, I will ask you, is it real co-design, adding on some hardware in an already designed hardware? Another thing that I notice that sometimes is the co-design is just power or performance tuning. For instance, you know better than me that, for instance, all the microprocessor, the top performance microprocessor from Intel are using technologies. I made this example, XTU or similar performance tuning software to overclock some parts of the chip of the device or the system or whatever, in order to get more performance from some part of the chip of the system, and less performance from other parts of the chip or the system. So this is something that is optimizing the performance and the power supply of the device. But I would ask you, is it real co-design? I mean, there is some component. I mean, we are affecting with the software the hardware capabilities, and we stress the system, we overclock the system if needed, or part of the system if needed. But according to the definition that we had in the beginning of this presentation, I wonder if this is a real co-design. Another thing that I noticed that sometimes the co-design is just a trade-off between different co-design platforms that we can buy on the shelf, I would say. For instance, we can compare in this way different kind of memories and the performance of different kind of memories in relationship with the specific code, with the specific applications that we are going to run. Yes, it is an optimization, but as I said before, is it a real co-design, or is it just a trade-off between two different technologies? Another example, and of course, I want to stress in this slide that the co-design normally, I mean, from my point of view, is not just an add-on to the system. The real co-design hardware and software must be designed together and mutually and proactively influenced to be tuned to the specific application in order to get the best HPC computational and power consumption performance. So the two aspects of the computational and power consumption performance, my humble opinion, should be tuned together in the co-design fashion. And this is, I mentioned it also yesterday during the panel, if we think the next generation of supercomputing machines, the data scale, and we try to understand what is the trend. So the Denner scaling ended in the mid 2000 years. So basically, the system that we build, we design, are going to use more power. So the energy consumption will increase in the future, in my humble opinion. More powerful HPC usually means that they use more energy too. This is also a general trend that I see. Data scale, also according to some estimation from Jack Dongara and I mean the best people, the best thinkers in our field, thinks that the data scale will probably need hundreds of megawatts or even gigawatts according to some estimation. And I wonder if is that sustainable, because basically you need to have a power plant just for your HPC. So it is something very, very expensive, and it will affect also the environment and everything. I mean, since we have the Green Deal as a priority of the Union, I just ask, is that sustainable? Another thing that I noticed from my privileged point of view is that the computing-intensive data crunching move from the CPU to the accelerators. This is a general trend. So the CPU contributions is nearly irrelevant in most of the cases. So the accelerators is playing a dominant role in the computing performance. And we have a different kind of accelerators. So I mentioned a few of them, but we have a lot of different kind of accelerators that we can use. Some of them are extremely expensive and very difficult to integrate in the ordinary system. For instance, the quantum processing unit, the QPU, is a very peculiar accelerator that normally does not match very well in the same HPC system for several reasons that I'm not going to analyze now. So in some cases, the accelerators is also something very difficult to be integrated in the HPC. I noticed a strong malleability of the applications. Of course, there is the mixed precision that is taken into account in all our codes, I will say, after the DGEM publication of some years ago, everybody is taking into account that kind of aspects. The energy efficiency is a very important topic in all our systems, and there is a modular, highly heterogeneous supercomputers in place in our systems. So another trend towards the data scale is the data scalability that should be thought of towards data bytes. So it's we need to deal with a very large data sets, but in some cases we have highly heterogeneous data sets. In some cases, very small data set and very large data set at the same time, and dealing with the same application. The data location should be the closest to the data cruncher. I mean, the accelerator. The accelerator should be fed by the data in a very quick and very efficient way. And I noticed that sometimes it is not the case. The interconnection, normally, it is a system-based interconnection. So it is it should pass through, not always, but some, I would say in most of the cases, through the CPU. And I noticed that the more advanced design and the design in our field are using interconnections that are closest to the accelerator. So they prefer to use so-called bare metal computing also for the interconnection between the accelerator. We needed to have an open inclusion and dynamic use of new kind of accelerators, as I mentioned before, the quantum, the neuromorphic, and so on. So we need to keep our systems open to new kind of accelerators if they are needed. In this general context that I showed to you very briefly, the traditional work breakdown structure of the HPC integrated components may not be feasible anymore. So maybe the next generation of the HPC will not be a general purpose HPC, static fat nodes as usual, I will say. But rather than an heterogeneous data flow processing, dynamically reconfigured, tuned and tailored to the specific application or applications and related process and thread. So the trend, especially I noticed that in the private sector, where there is a company that has a specific problems to be solved, they prefer to implement a so-called mission-specific HPC. So the data flow through highly interconnected accelerator may bring active reconfigurable messages also. So the data could be not just data, but could bring also some messages, some code, I would say, that is able to dynamically reconfigure the hardware to the specific data flow processing. So maybe in the future, we will have a reconfigurable mission-specific APC. It is something that I just put on the table, I mean, as an idea that we maybe consider for the next generation HPC. I guess that this is my last slide. Thank you for your attention and thank you for all your contributions that I attended in the morning. Very interesting. Thank you very much.
Thank you, Matteo. Let's thank our speaker and ask him a few questions, perhaps. Who would like to ask first? Please go ahead.
Thank you for the presentation. I have a quick question regarding the zeta scale. For me, it's a bit of a controversy because even with this exascale machine, we are measuring the number of floating point multiplication for the HPL benchmark.
Yes.
Scientists, they don't care about this. The most, a closer benchmark will be the HPCG. And for the HPCG, it's, 1% efficiency of the machine today. So zeta scale, even exascale for HPCG will not be reached anyway, anytime soon. So I don't believe zeta scale is a relevant target for the future. Because it does not, I don't believe it makes sense for the scientist that will use the machine. Do you think there is another target that would make more sense than zeta scale or even exascale nowadays?
All right for the benchmarks, but the benchmarks are not. The real world is facing some real problems that needs a real application, and in some cases, and also during this workshop, some example have been shown. The needs of highly computational power in the system is highly demanded, I would say. So it is really needed for some specific application to have a very powerful machines. The computational power should increase in order to be able to tackle some problems that at the moment are not tackled in the right way. In the plasma physics, for instance, or in space simulations, we have some examples that show that in having a most powerful the best HPC available on the market will improve our knowledge of the scientific topic and all the related fields. So I think frankly speaking, I do think that the having more computational power will be highly demanded in the future as well. So I think that the data scale or the post as a scale, call it as you wish, should be tackled by the scientists, by the technology that we design.
Further questions for Matteo?
Yes, I am wondering how many years do you consider to do such new system? It's not short term, it's middle term, long term?
We should, of course, there is the improvement in the technology and in the next future. At the moment, we already have in place some post-exascale systems, also in the US, beyond the European Union, I would say. So it is the post-exascale is already a problem, I would say, and something that is already in place, and some my colleagues, our colleagues, technologists are addressing this problem. And for the zeta scale, I mean, the near future, in 10 years, who knows, we need to have this kind of power, computational power in order to address some specific problems. Of course, this means that, as I mentioned before, with the traditional way of thinking, the HPC will require most probably millions of processing elements in the system, or billion even. There are some estimation billions of processing elements in the system, and that's the reason why I highlighted some problems related to the system designed that way, in a traditional way of assembling processing nodes together in order to achieve a higher performance. And that's the reason why I put it on the table that maybe we should consider something different in order to tackle the same problems that at the moment we cannot tackle because we don't have enough computational power, in a different way, maybe with a more mission specific HPC specifically tailored, so co-designed to the specific application that we want to tackle, to put in run and then tackle the problems, the specific problem that we had in mind.
Okay, thanks. So around 10 years.
Yeah, I think so. Yeah, maybe. Who knows? I mean, it's something, of course, the technological trends, we can just estimate something that is going to happen in the future, but who knows in the details of this of this next machine that we are going to design.
Matteo, a comment from my side. So based on what I heard from you yesterday and today, so you consider post-exascale, first of all, feasible, but to get there, we need to focus on a mission or a set of related, let's say, domains. Is this accurate? It's obviously not a complete
Yes, yeah.
capture. Right.
Yes, I think that this is my humble opinion. I stress it again because I think that maybe we should consider to, especially because we have different accelerators and each accelerator can tackle specific problems. So I think that the general purpose HPC, this is my point, the general purpose HPC at the zeta scale level, so the post-exascale level, should be is going to be very expensive, very complicated to manage, and maybe the general purpose HPC cannot tackle in a very efficient way the problem that we need to tackle. So maybe we should consider to co-design the specific high-performance computer to the application that we have in mind. So every set of applications, for instance, plasma application should be tackled, just to make an example, with a specific mission-specific HPC, where all the accelerators are tailored and the whole ecosystem in the interconnection, the data set and everything is very tailored to tackle the specific application in a very efficient way from the point of view of the computational power, but also from the energy consumption point of view.
Right. I think you made it clear. So my follow-up to that is that we can anticipate, as you say, we already have accelerators that seem to be very successful or very relevant for one type of computation, but perhaps are not applicable or effective for one type of different type. So I guess based on your mention of the data flow paradigm, we also need, seems that we need advances in what an operating system is, right? An operating system does not take any preference, does not show any preference to the applications, offers layers of abstractions for applications, etc. Now, I know there has been this initiative of meta operating systems, which are really flexible resource managers, more dynamic in timescales. So I guess your full, shall we say, view includes such a layer. I have, because let's say I am operating a supercomputing center and I need to support two domains, let's say plasma physics and I don't know, material science. It might need that I have two distinct collections of hardware resources and I need to make them available under policies, under perhaps billing models, etc. So in my mind, this has a lot of work in the system software layer and also in the, shall we say, flexible allocation and deallocation. Is this compatible with what you have in mind? Do you have in mind something that is, shall we say, more hardware focused? So a custom built machine for application A and a custom built machine for application B, or a mix and match functionality closer to what I was trying to outline? For my curiosity, mostly, it's not a commitment from your side, right?
Yes, I think that you mentioned some operating system that could be used, exploited in the system in the future. Of course, we need a CPU anyway in the system. I mean, a cluster of CPUs in the system because the accelerators alone cannot. I mean, can work, but it will be nearly impossible to manage the whole system without a CPU in place. So the CPU will control all the various accelerators in my idea, my humble idea, anyway. But I noticed that sometimes the so-called bare metal computing is in place. So sometimes the accelerators is just running the code very efficiently without any kind of operating system, and so also that aspect could be considered in order to be extremely efficient. As I said, also mission tailored. I mean, mission specific application. Basically, they do not need to have a huge infrastructure of software, but everything, also the software, is tailored to the specific application. So, of course, as I said, we can think that the CPU is running a traditional, I would say, layer software stack made of several layers, but maybe the accelerators are going to run a very specific software, very basic sometimes software, in order to achieve the highest performance from the whole system, I would say.
Okay, thank you for the follow-up.
Thank you.
Anyone else to ask a question to our speaker?
Hi, and thank you for your presentation. It was excellent, and I think it is worth having a longer time just to go deeper into the subject because it's very important, I think. I have maybe one remark and questions for you about the mission-specific HPC clusters. We have a few examples from the past, like the NEC SX429 supercomputers, who are massively vectorized with a long vector size, and they were tailored for computational fluid dynamics.
Yes.
And there is also the IBM Blue Gene P, which is tailored for QCD, quantum chromodynamics.
Yes.
So they both disappeared, and now we have these general purpose CPUs, ARM and x86, which are not tailored for specific applications, but we have seen some instruction that were implemented in these general purpose CPUs, like the square root, like it's not for the, and the next one is not for HPC, but the security instructions
Yes.
improve the HTTPS or SSL protocols. And the last instructions, which are the gather scatter for a vector, and this is more for the plasma physics, and because you have indirections in this, so we have new instructions. But don't you think that we must rethink the architecture of a CPU, like the length of the memory lane, like when we ask for a data coming from the memory, we have 64 bits coming from the memory. Maybe we just need not 64 bits, but bytes. So why don't we rethink this and just take bytes per bytes, or 8 bytes per 8 bytes, or something like this? Don't you think that it will improve the codes in plasma physics, even for in general purpose CPUs, or not?
Yes, you make a very good example. I mean, in some cases, for instance, we need to have specific instructions in the CPU architecture or in the accelerator architecture in order to tackle in a very efficient way the problem. And in some cases, for instance, we needed to get the memory, to have a very efficient memory access and maybe tailored to the specific application that we are going to implement. So in this case, with the traditional HPC, basically you buy the hardware as it is and you install it. And if you need to get access, for instance, to 16 bytes instead of 8 bytes per access, per memory access, it could be difficult to implement because the system has been designed that way. Basically, you need to take it as it is. But if you design the system tailored, well tailored, so co-designed on your specific application or set of applications, you mentioned the plasma physics, for instance, it could be a sector that could be tackled by a specific mission HPC computer. You can think of these so-called details. I mean, the memory access, the accelerator, the kind of accelerator that you need, the data set, the specific instruction. I mean, if, for instance, in some cases, you don't need to have the floating point at 64 or even more bits implemented in hardware that is very expensive. Of course, it requires a lot of silicon in order to be implemented in the CPU or in the accelerator. So you can do it in hardware, in software instead. So these kind of aspects could be tailored if you know the kind of application that you want to run. And as I said, you mentioned some machines that were tailored to the specific application that now they are not in place anymore. You are right. You are right, because in the past, some stage that technological improvement was so high that and also the software control of thousands of hundreds of thousands of processing elements was in place, so we were able to control the system very efficiently, to provide the access to this huge HPC environment to some specific and different applications very efficiently. But I wonder if in the future, I'm not saying now it is that is the best that we can do, and it is very efficient to have a very large machine installed in one place, and then you get access to the machine and you run your code. Now this business model is perfect, I would say. I mean, it's very efficient. I just telling you, is it, I'm asking you, is it efficient, very efficient for the next generation of the HPC that we are going to design? So for the post-exascale, I just think that maybe we should reconsider our way to design, to co-design the software and hardware to the specific application. This is just an idea that I put on the table, but maybe I'm wrong. I don't know. But maybe we should reconsider, especially because of the diversification of the accelerators. I noticed that sometimes you need a specific accelerator in order to run very efficiently that kind of application. So if that is the case, it will be very difficult to have a traditional HPC with all these kind of different accelerators in place, maybe most of them are idols because they are not tailored to the specific application. So you need just to use one specific accelerator for that application. So if that is the case, maybe a reconfigurable hardware could be considered and tailored to the specific application that you need to run. This is my idea that maybe could be wrong. I'm not saying that I'm right. I'm just thinking the future and asking you, maybe it will be not the same, the HPC of the future, because of these new kind of technologies that are emerging.
Right. Let's thank our speaker.
Thank you.
We appreciate all this food for thought.
Thank you very much.
Hello.